Back to my YouTube channel. In this video, we're given example 4. Says determine the following. Sort about this. Sort about that. Says determine the total force Ft, the total force there, and its point of application in the system. In figure 4.5 below, we've given a density of fluid which is 800. One, the total statistic force, hydrostatic force, and its points of application given two spheres, two cones, not cone, I want to say, yeah, given these two type there, two objects like that, right? Since you've given these two cylinders, you've given two cylinders, I've given two cylinders. We are used to one cylinder, but now here we have given two cylinders. So guys, let me zoom in a little bit so that you may, if you're given two cylinders, guys, you know, from here maybe we must have some, you know, hydrostatics will act there. We'll have F1, hydrostatic force 1. Considering this, if we can actually, we have, this is the same as, we can call this we have sphere 1 there on the top, cylinder 1. I am keeping say sphere, sorry guys, cylinder. Then you have cylinder 2. We have two cylinders. So first start by the bottom one. Always start by the bottom one, this cylinder that I will highlight. Start by working on with the cylinder. Use what you know. You'll start by working with this. However, because now we're given a force that is acting on the cylinder 1, we can start by that cylinder 1. We can calculate only the force there. We've given the pressure, so we know that if you've given the pressure, we know that force, we've given the pressures in it. No, we know that force, I can call that force, yeah, I can call it force, because I said that it's 1, I'll call it force 1. Whereby there I have no force is it is pressure multiplied by area, isn't it? Pressure multiplied by area. We have our pressure, but the area, remember, the area here will be pi d multiplied by the height. But now you'll say total height. Why will be a total height? Remember, this is a fluid. This pressure that will be exerted on the cylinder 1 will also exert a force on the fluid 2. So for calculating, you will consider the total, for you're supposed to use the total height. Use the total height always when you're calculating your length. They will consider of this all if you are focusing on the first cylinder there. That is what you're supposed to know, because we'll exert the force there, will exert the force on the bottom fluid. So that is our area. This will be density multiplied by pi multiplied by d multiplied by ht. Then here we have that to be, we've given 8 kilopascal, right, times 10 to the power of 3 multiplied by pi. The diameter, you know, is 0.6 meter. This is 0.6 multiplied by the total height of the cylinder, which is total 1 is this. You sum up the 2 is 1.4. This will be 1.4. Then if you punch this is what we'll have there. 79,168 kilonewton. This is in kilonewton. This is what you will have so far. We don't know. That is what we'll have. That is what you will have. So now my question is this. Remember, we are focusing on the side. I've explained that the hydrostatic will be acting it's supposed to act on the side of the, remember when we're having our beam, we'll act here on the side supposed to act there on the side. I've highlighted so this F1 is, we've taken it from the top part of the cylinder. It's a layer, but now because it's on the top, this fluid will also exert the pressure on this bottom one. So for us, we'll take the whole length, right? You must take the whole length when you are calculating now the whole length. Now our h bar, the center of application, for the first one, you must take the whole length and divide by 2. You see, you'll take the whole length and divide by 2. 1.4, you'll divide by 2. That will be our point of application for the first first force. There we'll take all the point of applications. Okay, let me just write the beam. Remember, you're supposed to have this. You said that is the side. You said you're supposed to take that. I've shown you guys. You'll have some, as I've told you guys. So the force will be acting. The first one, remember, is for the top cylinder. But now, because there are two, for the top one, you use the total, the sum of the two lengths, to find the, you can say H point of application from the top will simply equals to y bar. From the first one, we don't know. Let's say, let me say hydrostatic force will act maybe somewhere here. Let me just say somewhere here. F1, this is hydrostatic force 1, but must act on will act on H bar. Now will be exact as H bar. What I'm trying to say there will be exactly the same as H bar. You know what I'm saying. Our H bar will be like, it will be the same. Sorry, H bar, guys, I mean, will be the same as Y bar. For force 1, when you are given 2 layers, remember there we have 2 cylinders, the cylinder on top of another cylinder that has a fluid. If you have given 2 objects, you'll use that. If you've given the layers, if you've given 3, this will be equals to H bar. For the first one will be equals to H bar will be equals to Y bar for the total what Y bar for this for the object combined. So Y bar, we know that Y bar will be equals to the sum of this distance, all of this length, which is 1.4. Then Y bar will be equals to 1 1.4 divided by what? By 2. Then but Y bar is equals to H bar for the first stuff. So anyway, if you may punch that accurately, if I can punch that 1.4 divided by 2 will give me 0.7. This Y will be 0.7. Yeah, but this is the same as what is H bar. From what we take this from the top part, from the top. So this is what we'll have. So our force there, we'll have that force going down like this till like that. We'll have that to be 0.7 from the center of the point of application from the top there. Like that. That is the point of application. Will be 0.7 meter. Right. We are done with the first part. Now that we are done with that first part, we're done with that first part. So what about now? What about what about, I wonder this hydrostatic force, it is accurately or yes, it is fine. I wonder now, okay, that was the force one that was applied. So I want us to find what this guy, the hydrostatic for object 2. We have done with object 1 with the cylinder 1, but now for cylinder 2 here will be the same. We'll focus on the cylinder, now. For the first cylinder, we know, ignore the top part. For the second cylinder, ignore that part and focus on the cylinder. We know that our point of application now will be from the bottom until somewhere, we don't know which part there. Now when we're calculating if we're calculating the hydrostatic force for object 2, we know the hydrostatic force is density. Remember, this is a hydrostatic force. I'll just write that, or you can write hydrostatic force is density multiplied by height, area multiplied by y bar. So for this first one, we know we have here 800 multiplied by 9,81. The area will pi diameter, which our diameter is 0,6 y bar. For this part now, we won't use total y bar. Y bar will consider, remember, only this part. Like we'll take only the cylinder. Y bar will be 1.2 divided by, will be h minus 1.2. Remember y bar is equals to h minus 2. If we're considering that, will be 1.2 divided by 2. So if we find this hydrostatic force, what will be the value there will be 10.65 kilonewtons is h. It's hydrostatic for object 2. Now let us check its point of application. You can say from the top or from the bottom. The center point of application for this object 2, maybe you can say from the bottom or from the top. It's up to you. From the bottom, you must know it's 1/3 h, right from the bottom or from the base. Then from the surface will be 2/3 h from what? The top or from the surface. So it's up to you. This is 1/3. Then h there, consider that our h there, consider only this one, not the total one. This one is 1.2 multiplied by 1.2. What is the value there? 1/3 multiplied by 1.2 will be 0.4 meter. From where? From the base. If you want this one, will be 2/3 2/3 into 1.2 will be what? 1.2. This will be 0.8 meter from the top or from the surface. It's up to you, which one do you prefer. If you use the beam, I'll take the one from the base. Here it's our beam. Here it's our beam from the base. Here it's the base from the bottom. I will go upwards a certain length there. I will have this force applying, or let me see, let me just estimate that distance. Maybe it's like here till maybe somewhere here. I will have another force there acting in that direction. This is what it's F2 now, hydrostatic 2, right? But the total length of this beam, let's not forget the total length of this cylinder side. Remember, until there it was HT, right? Which is we've given that HT, it's equals to what here? 1.4. This is 1.4 meter. So this distance from this is what is 0.4 from the bottom here. We'll have 0.4 meter. So yeah, guys, now you can take the total force, what will must act in there. We don't know its application, its point of application. Let me say like this, the total force. Now they say we should calculate the total hydrostatic force. You can say will be F1 plus F2. We don't know the distance. Let me take it from the bottom. It's up to you which one. You can say X bar. We don't know that distance where exactly the total hydrostatic force will take place. This is what we'll have so far. Understand? So this is what we'll have so far. But we know the values of this one. We've calculated, and we know the values of this one. It's a matter of applying. F1 we know, and F2 we know. We had that F1. We had F1 to be 9.168 kilonewtons. This is in kilonewtons. Then 2, it was 10.65. This one, it was 18 kilonewton. So far you take up the moment now. The moment from the about left, moment about right. Now it's a matter of you to take up the moments. Right. Now take up the moments. You have to take up the moment. Oh, right. So you can take up the moment. Let me do this so that you won't be confused. Let me remove these things that I've written. This is F1, the force of F1, the force of F2. There. So yeah, let's check now. Apply the beam. You can see the sum of the moment acting on the right must be equal to the sum of the moments. Must be equal to the sum of the moments acting on the left. So we can take the moment. Where can we take the moment? About what? So we can take the moment from the top. Remember, here we have, this is top part. Here we have this, it's a base. We can take the moment from the top. Take a moment from the top. We will take moment from the top. So if we take moment from the top like that, as you can see, F2 will be equals to what? to 0.5, and this distance, what will be this distance, guys? That little distance, remember the whole distance is 1.4. Here we have 0.4, here we have 0.7. What is the remaining? We'll have 1.4, then I subtract all of 0.7 and also subtract 0.4. We'll be left with what? 0.8. Yeah, this is 0.8. The distance here is 0.8. Okay, 0.8 meter. So yeah, if I take the moment from the top here, this will just be, I'll take the moment up from the top here. If I take the moment from the top, that will act as a support. Then I will have the distance from F2 will be F2 multiplied by the distance from the top until F2, this distance until here will be 0.7 plus 0.8. Right, then we write F2 will be multiplied by the length from the moment that you've taken there, which will be 0.7 plus 0.8. 0.8 plus 0.7 would be 1.5. Right, force that are acting where on the left is some of the force acting on the left. We take in the moments plus multiplying the moments. Now we can come to F1. This is still acting on the left. As you can see, the arrows facing on the left, on the right, the one that are acting on the right. See the arrow. See also that's the acting there. So F1 will be from the top until F1 is 0. What? From the top until to F1 we have 0.7. we'll have F1 multiplied by 0.7. This will be equals to the one that acting on the left, which is this total force F2 plus F1 plus F2. We took the moment from the top, the distance there. What will be the distance? We don't know. Also from the top we don't know the distance here. I don't know that distance. Right, I don't know that distance. Why don't we just, let me call this the top one. Since I've taken that, I can call it y bar, x bar, the top one. I don't know that distance. Right, so since I don't know that distance, then I can say F, they will have F1 plus F2 plus F2 F1 plus F2, right, must be multiplied to what? The distance there we don't know, which is x. We can call it x. From the top we don't know that distance exactly where it is acting. So F1, F2, we've calculated F2 is unit, which is 10.62. It was in kilonewtons. So multiplied by 1.5, right, multiplied by 1.5 plus F1. What was F1? Was 70 what? 79. What 71? 70. Remember it was 79,168. Then multiplied by the 0,7 that we have there would be equal to total force 10,62 plus 7, 9. Let me just write it here on the side. Total force T1 plus T, F1 plus F2 will be equals to what? 10,62 plus 79,168. So what this will be 89,81. Okay, this will be 89,818. Multiplied by the distance x, but here we don't know. Then on our left hand side, you can punch this, all of that. Let me check. You can say 10,62, right? 10,62 multiplied by 1,5 plus 79,168 multiplied by 0,7. This will be 71. 3,3476 is equals to 89,818. Then divide by this, both sides. I punch this on the calculator. I'll have 71,3476 divided by 89,818. This will be equals to 0,794 meters from the top. We have the value of x from the top, so that is how it goes about. So we have this point of application x, that is what we wanted. Total force, the point of application, we got that. So that is how we go about calculating these values, guys. So thank you for watching. Please do not forget to subscribe to my YouTube channel and click the notification button so that you'll be notified whenever I post the new videos.